Hello and welcome to Lecture 8 of Embedded Systems, in which we shall cover sampling and analog to digital conversion. The entire process of analog to digital conversion may be best understood as a composition of two processes, one of them being the sampling, the other one is the quantization. So let us first try to understand what do we mean by sampling. Sampling is a process to convert a continuous time or analog signal into a discrete time or digital signal, but the requirement of digital signal will be met when we also perform the second step, that is the quantization. So in other words, you can try to envision sampling as a process of converting this continuous time signal or the analog signal into the dots, which is analogous to recording the values of the signal at discrete instances. So for example, here we can see that the signal value has been recorded at time instance 0, and then the signal value is recorded at time instance 1, but not in between. So essentially we are recording the value of the signal at discrete time instances, which in this case are the integer multiples of unity. Once the signal is sampled, it is then called as the discretized signal. The requirement of a signal to become a digital signal will be met when we perform the process of quantization, and that's where the analog to digital converter module inside the microcontroller needs to be configured. Before proceeding, it is important to note that once the signal has been sampled, then the highest and the signal has been sampled at the sampling frequency fs, then the highest frequency component that can be recovered from the analog signal is half of the sampling frequency. And we should also note that in real life application, we can only record finite number of samples of a signal, even though theoretically the signal duration is infinite. Now we move on to the quantization process. So quantization process is reducing the infinite precision to the finite precision, enabling our processor to store the data. In other words, once we have sampled the signal, we then proceed to map the analog magnitude of the signal that has been stored into one of the several digital levels. So with the help of an example, let's consider an example of a 12-bit ADC, as we shall discuss later in our lecture. It's a 12-bit ADC, which means that it can represent any analog input value with the help of 2 to the power 12, which is 4096 different levels. I would call them digital levels. So that's the process of quantization. So here in this graph, we can see that we can have a continuous range of analog voltages between 0 to 3.3, assuming that this is the maximum value of the analog input voltage which we can quantize. And in the terminology, in the diction of this lecture, we can just say we are going to convert this analog input voltage sample into a digital level, and we can have as many as 4096 digital levels, starting from level 0 up to 4095. So overall 4096 levels. And we can assign each level, we can represent each level with the help of a decimal number here, or a binary number. In computer language, everything must be processed as. So once the analog input is converted into a digital form, so that it is mapped to one of these levels, one of these 4096 levels, it can be stored and then processed further. So that's the process of quantization. But really, in this lecture, we are going to use the word quantization synonymously with analog to digital conversion, but you should always be aware of the fact that the analog to digital conversion is a process which includes sampling as well as the quantization. One of the attributes of the quantization is that we can always apply quantization to a finite range of input voltage. So in this case, the supply voltage given to the microcontroller is 3.3, so that defines the upper limit of the analog input voltage sample which can be converted into digital value. And that also brings up another observation regarding the resolution. So here we can define resolution as the maximum value of the analog input voltage sample divided by the number of digital levels. That's 4096. So 3.3 divided by 4096 gives us 0.8 millivolts. So what is the significance of this value? Well, this is the minimum. So this is the minimum voltage that can be digitized. So this is the minimum voltage value that can be discriminated and digitized, and any value less than that is either not understood or discriminated or digitized by the microcontroller. So that defines the lower limit. In a sense, this 0.8 millivolts defines the lower limit or the lowest voltage that can be inputted to the ADC. This 12-bit ADC is an internal hardware module on your microcontroller board. You can also interface a higher resolution or a high-speed ADC depending upon your application, but we shall restrict our attention to the 12-bit ADC that is an internal hardware module of the microcontroller. Now we're not going to discuss different types of analog to digital converters in details. In fact, we are going to restrict our attention to a brief discussion of a special type of ADC that is located inside your microcontroller. It works according to the principle of the successive approximation ADC. The most important thing to understand is that this specific type of ADC is a sequential circuit, and it takes multiple clock cycles to convert the analog input voltage samples. So remember, this is the input. It's an analog input. It is an input sample. And here, the output of what we call as the successive approximation register, which is trying to approximate this analog input by means of an n-bit digital output, D0 through Dn. And once an adequate approximation has been reached, then the successive approximation SAR register signals the end of conversion. So that is achieved. That happens when the EOC, the end of conversion, is set to 1. Now, in each cycle, the current digital output is converted into an analog value by the means of an inverse process, the reverse process, which is carried out by DAC, the digital to analog converter. So the digital to analog converter accepts the digital input, which is over here. So remember, this is the input, the digital input to the digital to analog converter, and the output over here is analog. So corresponding analog value of this digital input is then compared by the comparator, and if they are sort of close enough or equal, then we can this successive approximation register can send a signal of it's a signal telling us that the conversion has been attained. But if they are not close enough, then the whole process repeats and it takes multiple cycles, but not more than n cycles. So within an n cycles, the successive approximation analog to digital converter should be able to convert the input analog voltage sample to the output. So here is the output, which is an n-bit digital output. It's an n-bit digital number. An important component of the analog to digital converter described in the previous slide was the sample and hold circuit, represented by SH block, whose input was Vin. Essentially, what this component does is that it converts an analog signal such as this into its staircase version, such as such as the staircase version of this might look something like this. So this is going to be analog input AI, the input to the sample and hold, and this AO is the output of the sample and hold circuit. And why do we need this sample and hold circuit? Because we want to hold the value of analog input voltage sample for some time before the next sample arrives. So it is important to hold the value, and that's why we're going to make a staircase approximation such as this. Let me now describe some attributes and parameters of the ADC on the microcontroller. The very first thing to note is that it has an internal voltage reference, 3.3 volts, the maximum voltage at which we are going to run our ADC. What this means is that the 12-bit ADC should output the maximum 12-bit value, which is hex FFF at 3.3 volts, and the minimum value hex 000 at the minimum analog input voltage, which is 0 volts. And we saw previously that this gives us a resolution of 0.8 millivolts, which is obviously less than 1 millivolt. However, one should note that this is more like a theoretical resolution. In practice, however, because of the noise in the analog input voltage, and the noise can be much higher. Noise can actually be much higher than 1 millivolt. So the practical resolution may actually be dictated by the noise, and it may be the case that if the noise, if we assume that the noise is around 10 millivolts, then our ADC input must be at least 10 millivolts or higher to give us a reliable output. We can always think about improving the signal to noise ratio. Essentially, this SNR, or signal to noise ratio, is a ratio of signal power to the noise power. And this can be done by slowing down the ADC, by running the ADC at a slower clock, takes longer to sample, apply some sort of a filtering ground shield. There is, however, a built-in noise cancellation process. We call it a digital filtering. What it does is that it takes an average value of multiple samples, and by averaging, when we average multiple samples, the noise, if it has a special property such as a zero mean noise, so this really assume the noise is a zero mean noise. If we assume that the noise has a zero mean, then what it does is that it averages out the noise. So this signal to noise ratio can be increased when we take the average of multiple samples. So our ADC collects 64 samples for one. So one user sample is an average of 64 real samples. So it is an average. And by means of averaging, we can hope to lower the noise level and possibly improve the effective resolution of the analog to digital converter. So this averaging is a built-in feature, and so this is a built-in feature of the ADC. More attributes of the ADC. Uh, the ADC can accept input from 12 different analog input channels, single-ended as well as differential input configuration, on-chip internal temperature sensor, a sampling rate up to 1 million samples per second, flexible configurable analog to digital converter, and it can have as a programmer you can utilize up to 4 programmable sample conversion sequences from 1 to 8 entries long, with corresponding conversion results in the first in first out hardware buffers. Flexible trigger control. Now this is one of the most interesting attributes in my opinion. What this means is that you can start the analog to digital conversion as soon as, but by several different ways. So you can initiate, you can tell your microcontroller to initiate analog to digital conversion by means of a software trigger or timer, by means of the analog comparator trigger, pulse width modulator trigger, or it can be a trigger at the GPIO ports, or it can be just the continuous triggering. Also, as we discussed before, that it has a built-in noise reduction feature, which allows us to have an average value obtained from the 64 samples. So one analog input voltage that we are sampling is actually an average of 64 samples. It's an average of 64 samples, and that averages out the noise. And yes, internal voltage reference 3.3 volts. That's we have discussed already. Now this complicated figure describes the detailed architecture of the ADC, and you can see there are several hardware blocks which are connected by a complex logic. But the good news is that from the programmer perspective, we can come up with a simplified representation that allows us to better understand the functionality as well as the configuration of the ADC, so that you can know exactly what are the relevant registers and the bits and how they are required to be set for the desired functionality of the analog to digital converter. So here is the functional description and a much simplified snapshot of how the ADC works. Essentially, we have 4 sample sequencers, and their detailed description will be available in the next slide. But here, you can assume a sample sequencer as kind of a parallel to serial registers, which works on the analog inputs. So these are the analog inputs. They are available in parallel, so we can just say these are parallel analog inputs. Because we have just one analog to digital converter. So actually there are 2 ADCs on your internal ADCs on your microcontroller, but we are, let's say we are looking at ADC number 0 module. We are working currently with ADC 0. So there is just one analog to digital converter that's called ADC 0. Therefore, we cannot convert all these parallel analog inputs simultaneously to the ADC. We cannot do that. We cannot, so that parallelism is lost. We cannot do that. There's just one ADC. So what we do, and what the a sample sequencer does is that it serializes. So the output is serialized analog inputs, and these are going to go into the priority multiplexer first. And why do we have this multiplexer here? Because we have analog inputs coming in not just from sample sequencer number 0, but also the other sample sequencers such as sample sequencer 1, sample sequencer 2, and sample sequencer 3. So there are in total 4 sample sequencers, and 2 of them have 4 inputs, sample sequencer 1 and 2. One of them has just 1 input. So if our application is very simple, requiring only single channel, so we might just want to use sample sequencer number 3, and we shall discuss in detail how to use how to activate or deactivate sample sequencer. So and then obviously sample sequencer number 0 is the largest one. It has 8 analog inputs. So it is possible that we require multiple sample sequencers, and there might be a conflicting situation where two or more sample sequencer want to forward their inputs. Let's say sample sequencer number 0 wants to forward its analog input, and also sample sequencer 0. So who's going to go forward then? The question is whose output should be forwarded to the ADC. Well, that's where the priority multiplexer becomes handy. So this priority multiplexer will decide should it be sequencer 0 output to be forwarded to ADC, or should it be the sequencer 1 output to be forwarded to ADC. And therefore we can sort of set the priority levels. So this is run by the priority levels. It's very similar to the priority levels for the interrupt sources that we described in the previous lecture. Nevertheless, depending on the priority level, the corresponding the sample sequencer who has the higher priority will the output of the sample sequencer with the higher priority will be forwarded to the ADC. So for example, if the sample sequencer 0 has the higher priority, its output will be forwarded to the ADC, and then that's where all the serialized analog inputs will be digitized, and they are going to be stored in the corresponding first in, first out buffer. So I'm going to discuss these in more details in the upcoming slides. Here, the final thing to note is that we have 8 parallel analog input voltages coming into sample sequencer, and even though these are going to be serialized before being sent to the ADC, but the final data is going to be stored again sequentially. But then there are going to be 8 entries in the corresponding FIFO buffer. So the number of inputs on the sample sequencer is the same as the number of entries in the FIFO buffer in the corresponding sample sequencer. So how does a sample sequencer actually work? Let's take a look at this example of sample sequencer number 1, whose input currently contains 4 voltage samples, V1, V2, V3, and V4. And these samples, as I discussed before, are actually available in parallel. So these are coming from 4 different sources. They are available at the inputs of the sample sequencer at any time instance. What a sample sequencer does, in this case, sample sequencer number 1 does, is that it is going to serialize the samples so that V1, V2, V3, and V4 are serialized, so they are serially outputted and form a sequence such that V1 will be sent first. It is going to be forwarded to the MUX or then to the ADC. So V1 first, then V2, then V3, and V4 will be the last one. The analog voltage samples from the sequence after being digitized by the ADC are then forwarded to the first in, first out, or FIFO buffer. And in this case, it is the sequencer 1 FIFO buffer. And these are going to be stored in the same order as that of the sequence. From the programmer's perspective, the ADC FIFO buffer is going to store this data automatically in the given order, and we don't need to worry about explicitly or even implicitly programming ADC FIFO buffer for the task. The digitized analog input voltage samples are now available in the FIFO buffer, and we can retrieve them one by one. So for example, we have to think about what is going to happen if we read the FIFO buffer once. So just when the data is stored in the buffer and the first time it is read, what we obtain is a digitized version of voltage V1 shown here. And this item will be removed from the buffer and all remaining items are pushed down. Hence, they look like this. And if we do another read, we get a digitized V2. This item is now retrieved from the buffer, and the remaining items V3 and V4 are pushed down. Read again, and we get digitized V3. And finally, if we read again, we get digitized V4 until the FIFO buffer becomes empty. Each sample sequencer can obtain analog input from as many as 12 different sources. We call them analog input channel, AN. And each analog input channel is mapped to a general purpose input I/O port. These are selected pins of the I/O ports. For example, the analog channel number 0 is available at PE3. Analog channel number 3 is available at PE0. And analog channel number 12 is available at PB4. So when we are going to use the ADC, we'll have to explicitly tell which analog channel is connected to which input of the sample sequencer. And that's an essential part of the ADC configuration process. Alongside, the corresponding port pin needs to be configured as the analog input pin. So now we look at some of the registers which are used to configure the ADC. The first of them being the ADC clock enable register. The least two significant bits correspond to the clock enable of the two ADCs. There are two ADCs on the microcontrollers, ADC 0 and ADC 1. And we we can use the clock enable. We can enable the clock of the corresponding ADC by setting the corresponding bit to 1. So for example, if we want to use ADC 0, then the least significant bit will be set to 1. For ADC 1, bit number 1 will be set to 1. The next one is the ADC speed register, so to speak, ADC 0 PCR. The lowest 4 bits define the speed at which the ADC will convert the analog input voltage samples into the corresponding digital output. There are 4 values, one of the 4 values listed in the tables that may be specified for corresponding to the 4 different speeds of the ADCs, ranging from 125 kilosamples per second to 1 million samples per second. But one of the things you should keep in mind is that a low speed ADC might be important to increase the reliability of the analog to digital conversion, and that we discussed in the context of the signal to noise ratio. And in this table, the signal to noise ratio is increasing opposite to the ADC speed. Unless your application demands some minimum conversion speed, I would strongly suggest you to go for the low speed ADC configuration, such as this. The ADC trigger register, ADC0 EMUX R. The least significant 16 bits are important from our discussion. These are four 4-bit fields, each corresponding to the sample sequencer, starting from sample sequencer number 0, 1, 2, and sample sequencer number 3. For each sample sequencer, we can specify when or we can specify what is the trigger source. There can be as many as 10 different trigger sources. Therefore, we need 4 bits to specify the trigger source for each sample sequencer. So for instance, if we are interested in specifying the trigger source of sample sequencer number 0 to be the software start, that's what we are going to do in our lecture today, then we are going to specify hex 0 value in the first nibble. And already in the lab session, you have used a different trigger source, a continuous sampling one. And for that, it is going to be hex F. So another example would be if we are using just one channel as an input, then we might be interested in just using sample sequencer number 3. And as was the case in your lab exercise, the trigger source was always, which was the continuous sampling trigger. Then you simply assign hex F to bit number 12 through 15. However, note that there are so many other trigger sources coming from the comparators, from external port pins, the timers, and PWM completion. Now, once the sample sequencer is configured to be triggered by the software, there are bits in the ADC0 PSSI R register that we need to set for the trigger to actually enable ADC to start conversion. So in other words, in order to actually initiate the trigger, if the sample sequencer 0 is configured to be the software start sample sequencer, then in order for a program to actually give yes signal to ADC to start conversion, provided that the other start conditions are fulfilled, which we are going to see shortly, then one of the requirements is that we should make the bit SS0 equals to 1. Now that was for the sample sequencer 0. So the least significant bit corresponds to the trigger bit of the sample sequencer number 0. That needs to be set to 1 by the program. And if it had been sample sequencer number 3, then you're just going to make SS3 bit, which is bit number 3, equals to 1. Yet, for a sample sequencer to actually make a sequence of the input voltage sample and send it to ADC for conversion, there is another condition that we need to meet, and that is the enable sample sequencer. We can actually enable or disable the sample sequencer by editing the bits of the ADC, ACT, SSR register. The least significant 4 bits correspond to the enable or disable will be responsible for enabling or disabling the corresponding sample sequencer. For example, in order to enable sample sequencer 0, which really means that we want to start sample sequencer 0, we're going to make the first bit equals to 1. So this is going to enable sample sequencer number 0. So sample sequencer number 0 will be turned on, and it is going to send send the sequence to the analog to digital converter, unless there is a conflict with other sample sequencer, but that is going to be resolved with the help of the priority, the sample sequencer priority register, which we are going to discuss in the next slide. But this register ADC0 ACTSSR is essentially the on-off button for the sample sequencer. Now, it is possible for multiple sample sequencer to send their sequence to the ADC simultaneously. So for example, if the sample sequencer number 0 wants to send its sequence to the ADC and also sample sequencer number 1 simultaneously, then whose sequence will be sent to the ADC first is determined by the sequencer priority. It's also going to represent the interrupt priority. And in this case, we have 3 priority levels, 0, 1, 3 priority values, 0, 1, 2, 3. And for that, we need 2 bits per sample sequencer. So bit number 0 and 1 of ADC SSPRIR register represents the priority of sample sequencer number 0, which is this guy. Bit number 4 and 5 represents the priority of sample sequencer number 1. The priority of sample sequencer number 2 is determined by bit 8 and 9, and that of sample sequencer number 3 is determined by bit 12 and 13. There are unused bits such as 10, 11, 3, 2, 7, 6, and 14, 31. Writing anything to these bits is inconsequential. It is not going to make any difference to the configuration. These are just ignored and do not make any meaningful contribution to the configuration. So, but the bits that we really do care about are 0, 1, 4, 5, 9, 8, and 12, and 13. So how does the sample sequencer priority resolve this conflicting situation? So if, for example, the priority of sample sequencer is 0 and the priority of the sample sequencer is 1, then we are going to enable sample sequencer 0 sequence to be put forward and then digitize. And once that is done, we are going to enable sample sequencer 1 to send its sequence for the digitization. Next, how do we connect the analog input channels to the inputs of the sample sequencer? Now, for example, if we consider sample sequencer number 0, we have a register for each sample sequencer. So in this case, we are looking at a register that configures the input channel to the inputs of the sample sequencer 0, and the register is SSMUX0. So this 0 corresponds to the sample sequencer 0. So likewise, there is going to be a different register such as SSMUX1 that will be for sample sequencer 1, but then that only has 4 inputs. Those can be referred in the textbook. Anyways, we have as many as 12 analog input channels, and these are available at 12 different port pins. Now our job is basically to connect these port pins or the channels to one of the inputs of the sample sequencer. So this mapping can be fairly arbitrary. We can connect a single channel to the multiple inputs of the sample sequencer, or we can attach different channels to the different inputs, whatever is dictated by the application. And because for each input of the sample sequencer, we have as many as 12 possibilities. We have 12 possible channels for each input. We have 12 possible channels for each input per input. Therefore, to accommodate all possible 12 inputs, we have 4 bits for input number 0. So this mux 0 really means input 0, 4 bits. So if I say 3 here, it means that I'm really connecting analog input channel number 3 to my input 0. And if I say hex or in decimal, it doesn't really matter, 8, then I'm really routing the analog input channel number 8 to my input 0. And same goes for input number 1. Any one of the 12 possible channels can be connected to input number 1. And therefore, again, to accommodate 12 possibilities, we have 4 bits. So this way, any channel can be connected to any of the inputs of the sample sequencer number 0. Same goes for sample sequencer number 1, but then we have then we can only do that for the first 4. We can only do that for the 4 inputs when we discuss sample sequencer number 1. These are not applicable. Next, we have some control bits for each input of the sample sequencer. For each sample sequencer, we have a different register to add those control bits. So let's take an example of the control bits for the sample sequencer 0. This is register ADC0 SSCTL0. That 0 again correlates with the sample sequencer 0. And if we want to talk about sample sequencer 1, it's going to be 1 over here. Therefore, in case of sample sequencer number 0, we have 8 fields, 8 4-bit fields. The first 4 bits correspond to the control bits for input 0. The next 4 bit defines the control bits of input number 1. And likewise, the last 4 bits are the control bits of input number 7, as shown here. Now, what do we want to do with the control bits? These control bits are very important, and they provide the essential flexibility to configure the ADC to determine the end of sequence, the mechanism of enabling the interrupt. That is, if we want to enable the interrupt on the ADC through sample sequencer, and also to be able to sample the reading of the internal temperature sensor. There is another control bit that can be used to sample the differential input that we are not going to discuss in detail. However, we're going to focus the remaining 3 for detailed discussion. The first of them is the end of sequence. So let us now try to understand what does each one of these bits will do in more detail. Let's take an example of sample sequencer 0 accepting input from only one of its input channel, and the voltage sample available there is V0. What a sample sequencer 0 is going to do is it is going to put that in a sequence, and the sequence again contains just the same sample, V0. And that is the output to be sent to the multiplexer and the ADC. and after that there is no sample. So essentially uh, the first sample is the last sample. In that case, these 4 bits, out of these 4 bits, the end 0 bit defines the end of the sequence bit, and this is, and remember, so these 4 bits correspond to the control bits of the input number 0. That's where V naught is coming. Then because V naught is the only sample, it is the last sample, so we are going to set this bit E and 0 equals to 1. If, however, we are utilizing 2 of the input channels of the sample sequence of 0, then the output sequence will look like this. And in this case, V1 is the last sample in the sequence, and that is the input number 2. So in that case, we are going to look at the control bits corresponding to the second input. So this is input number 1, the second input, and here we find the end 1. So we're going to make end 1 bit equals to 1 and end 0 is equals to 0, signifying that the voltage sample available at the second input, which is input number 1, is the last sample. In case of 3 input voltage samples, the last sample in the sequence is going to be V2, and we're going to make the N2 bit, which is bit number 9 of the register, set equals to 1, and the N0 bit corresponding to the first 0th input 0, and the N1 bit corresponding to input 1 are both set equals to 0. And if we're utilizing all 8 input channels of the sample sequence as 0, then the corresponding N bits of the first 7, starting from N0 to N6, are all set to 0, because none of them is the last sample except V7. Corresponding bit number 29, N7, is set equals to 1. And this is how we added the N bits of the N bit among the control bits of the sample sequencer. One of the nice attributes of the microcontroller is that we can utilize the internal temperature sensor reading and put that in the sequence. So in the previous example, if we are utilizing all 8 channels, then the corresponding output sequence of the sample sequencer 0 would look like this. However, if we set the bit number 3, the TS0 bit, which is the temperature sensor bit, if we set that equals to 1, what it does is that at input number 0, instead of taking input from the digital from the analog configured GPIO pin, it is going to take the voltage reading from the temperature sensor and apply it to the input 0 of the sample sequencer, and the corresponding output sequence will contain will substitute V0 with the temperature sensor voltage. Similarly, if we want to do that for the other channel, we are going to set the corresponding nth bit input n, depending upon what input we are talking about. We're going to set TSN equals to 1, and that can be referred to from the description of the control register. But note that this temperature sensor voltage becomes available only when the sequencer is triggered for the first time. So once we have set up the sample sequencer, we configured it, and we have set the temperature sensor bit equals to 1, then the temperature sensor reading will be available only for the first time when the sequencer is triggered for the first time. But whenever the sequencer is triggered for the second time and onward, then the input channel normal voltage available, the input channel voltage that was configured to come from the samples of the of some of the port pins, that will be available, and there is no temperature sensor, you see. So now we have just the regular voltage available from the port which is connected to the input 0. So even though the bit is still 1, but there is no temperature sensor reading. So the temperature sensor voltage is only available with the first time the sample sequencer is triggered. And finally, we have 4 FIFO buffers or FIFO registers for each for the 4 different sample sequencers, 0, 1, 2, and 3, and their corresponding FIFO buffers. Because the output of ADC is only 12 bits long, so we are going to utilize the least significant 12 bits of each FIFO register. And we discussed in detail how to read data from the FIFO register. You can always refer to the slides on FIFO registers that we discussed earlier for more details. Yet, the description of ADC will remain incomplete unless we discuss how can an ADC possibly interrupt the microprocessor when one of its sequencer has completed the analog to digital conversion and has stored the result in the corresponding FIFO register. There are 3 registers for configuring the ADC interrupts, and the way we configure ADCs to be able to interrupt microprocessor is through its sequencers. So for each of these registers, we have 4 bits which are relevant, and each one of those 4 bits correspond to the sample sequencer. So now let's take a look at these bits in more details. The first of them being the ARM bit. So recall the function of the ARM bit in the context of the interrupt. So when we arm a device for the interrupt, it means that the device is allowed to interrupt the microprocessor. And in this case, when we talk about the ARM bit, basically we are talking about the ARM bit for each one of the sample sequencers. The first, so the corresponding register is ADC0 IMR, the middle one. And if we want the sample sequencer 0 to be able to interrupt the microcontroller, we're going to set bit number 0, which is mask 0. That is the ARM bit for sample sequencer 0. If we look at the second bit, mask 1, that is the ARM bit for sample sequencer number 1. Likewise, mask 3 is the ARM bit of sample sequencer number 3. So note that it is the sample sequencer who is actually going to generate the interrupt, or to be able to interrupt the microprocessor. So if we want to arm the ADC for the interrupt, basically we are really asking which of the sample sequencers can interrupt the microprocessor, and their corresponding mask bit should be set to 1. Then we have the trigger flag, which is set by the hardware automatically. So in this case, the RIS register, row interrupt service, it's a trigger flag. It is set by the hardware once the output of the corresponding sample sequencer is complete. For that, we refer to the register ADC0 RIS register. Again, the least significant 4 bits corresponding to the 4 sample sequencer. So if a sample sequencer 0 can interrupt the microprocessor, that is, we have set this mask 0 bit to 1, then when the sample sequencer generates an output sequence to be for the digitization, and when the ADC has finished when the ADC has completed the analog to digital conversion and has stored the data into the corresponding FIFO buffer, that is FIFO buffer number 0, then this bit is automatically set to 1. So it is automatically set to 1 by the hardware as a trigger flag, signaling the end of completion. In some sense, it has a strong connection with the EOC signal that we saw earlier during the discussion of the successive approximation register. You can always go back to that slide for more details. Once the trigger flag has been generated, then we need to acknowledge the interrupt. And for that, as we saw in the case of the GPIO port interrupts, we want to clear this. So we want to make this 1 equals to 0. We cannot write directly to this RIS register. In fact, what we are going to do is that we're going to write the corresponding bit to the interrupt clear register. So this third register is ADC0 interrupt service clear, ISC, or interrupt source, interrupt source clear, I think. We set this bit to 1, and that is going to make this bit go to 0. So again, the trigger flag is indirectly cleared when the corresponding sample sequencer, or when the corresponding source is set, is armed and can interrupt the microprocessor, and when the analog to digital conversion is complete, then we need to clear the trigger flag, and this is you're going to write to this register to clear the trigger flag for the corresponding sample sequencer. However, before I conclude the topic of ADC interrupt, it is important to note that one can still trigger the end of conversion through other ways. That is, even if the interrupts are not enabled. So in other words, it is still possible for hardware to set the trigger flag that is in the row interrupt service register, even when the ARM bit, which is the mask N bit in the ADC0 IMR register, is not set. And this end of conversion notification is important for the synchronization with the remaining program. But how do we do that? Well, we can use an alternate route, and that's where the role of control bit, i.e. N, can be highlighted. And herein lies the solution, that if we set the i.e. N bit equals to 1, then even if the interrupts are not enabled, we can still receive the end of conversion notification through the INR N bit, that is the trigger flag. So this trigger flag will still be set to 1 even if the interrupts are disabled. So this is an alternate route to obtain the end of conversion information from the trigger flag. But that requires us to set the control bit IEN to be set equals to 1. Even though they call it interrupt enable pin, I think in order to avoid confusion, we can just say it is actually an interruption. Let's just call it interruption enable pin, although it does not correspond to the interrupt bit, any of the interrupt bit that we discussed in the previous slide. Remember, IEN is in the control register. It has nothing to do with the interrupts. It's nothing to do with the interrupts as such. It is not an interrupt ARM bit. So this IN bit is not an ARM bit. It is not an ARM bit. It is just a it provides an alternative route to obtain the end of conversion information, end of conversion notification provided by the INRN bit in the raw interrupt service register. That's it. The protocol of configuring the ADC sample sequencer goes as follows. You start by enabling the ADC clock. So in this case, we're going to use ADC 0 and then set the conversion speed. Then we set the sequencer priority by writing to the priority register. And now we want to think about which sample sequencer are we going to use. So for example, if we are interested in using sample sequencer number 3, then before we configure sample sequencer number 3, we are going to disable the sample sequencer. And that is the only wise thing to do. Just as we disabled the timer during its initialization, we apply the same principle here. We want the sample sequencer 3 to be software triggered, so we are going to 0 bits 15 to 12 of the ADC0 EMUX R. The initialization procedure continues by setting the input source by connecting the input source to one of the input channels of the sequence sequencer number 3. And we're going to specify one of those 12 possibilities in the 4-bit field, bit 0 to 3 in the ADC0 SSMUX3 register, where 3 corresponds to sample sequencer number 3. Then we set the control bits in the control bit register. The corresponding register is ADC0 SSCTL3. Again, this 3 corresponds to the sample sequencer number 3, and it has got only one input channel, therefore single 4-bit field. This one corresponds to the differential input. This one, the last bit corresponds to the temperature sensor. Both are disabled. The bits that we are going to set correspond to the end of sequence. So this is end 0. There's only one input, so that is going to be that input is the only input in the sequence, and this one is in interruption enable, and that is set to 1 because we want to obtain end of conversion notification. We want to obtain end of conversion notification through the through the RIS register, the bits in the RIS register. So we want to obtain the notification, therefore we are setting this bit equals to 1. We don't want interrupts, so the interrupts are disabled, and once everything is set up, then we are going to enable sample sequencer number 3. Let us now put all of the things that we have learned so far together in the form of a C code that first initializes the ports and configures the ADC. In this case, we are interested in connecting the analog input channel available at PE4, which is going to get connected with the sole input of the sample sequencer number 3. We're going to configure the ports first. In this case, we're going to enable the clock on port E, and we're going to wait for some time before the clock stabilizes. Afterwards, set the direction of PE4. We want to make it an input port, so we're going to clear bit number 4 of the direction register. We're going to ensure that PE4 is not a general purpose port. In fact, it has a special function or alternate function. And this is the most important instruction as far as the configuration of the port PE4 pin is concerned. So remember, we have to enable alternate function on PE4, and that can be done by setting the fourth bit. That's hex 10. Value is setting the fourth bit of the port E alternate function register. Then we disable the digital enable pin. That's attained by clearing the fourth bit corresponding to port E digital enable register. And finally, we want to input an analog voltage to the sample sequencer through PE4. That means we need to enable an analog mode select on PE4, and this bit when we want to set bit number 4, that can be achieved by the OR instruction in the assembly language, or equals to statement in the C. Once the port pin PE4 is initialized or configured, our next job is to configure the ADC. We're going to activate the clock on the ADC by enabling the corresponding bit in the clock ADC 0 clock register. And we're going to introduce some brief delay. These 4 instructions are actually dummy instructions. We could have introduced delay in a different way as feel appropriate. This delay allows the ADC clock to stabilize before we proceed to the remaining steps. Now, continuing with the configuration of the ADC, we now set the speed of the ADC 0. Remember, we are going to use ADC 0, and all of the registers to be described here on this slide correspond to the registers of ADC 0. So after setting the speed, and in this case the speed speed corresponds to the value hex 01, which gives us 125 kilosamples per second. Then we set the priority, and in this case the sequence 3 has the highest priority. That may not really matter in this case, the priority value, because we are going to disable all other sequencers and we're going to enable sequencer 3 only. In any case, before we set the other, because so right now we haven't yet configured the sample sequencer 3 explicitly. So from this instruction, this is the first instruction that is going to configure sample sequencer number 3. So before we actually configure, we want to turn off, we want to disable sample sequencer 3, and that's what we do with all the sample sequencers. The first task is to make sure that the sample sequencer is a software trigger. So we're going to write down to the ADC0 EMUX register, clearing the corresponding bits, and then we're going to configure, we're going to connect the input. So sample sequencer 3 has only single input, and we said before that we would connect analog input channel number 9, which is available at PE4 to that single input. And here is the instruction, here is the statement, C statement for doing that. We're going to set the control bits in the ADC0 control register for sample sequencer 3. And in this case, as we saw before, we're going to set the interrupt or interruption enable bit as well as the end of sequence bit, signifying that there is only one input in the sequence, and we're not going to use the differential input or the temperature sensor reading. For our example, we're going to disable the interrupts, so by clearing the corresponding bit in the IM register, and once everything has been done, it is now time to enable the sample sequencer so that it can start accepting the analog input samples. Here's an example of a flowchart that can possibly utilize the ports and the ADC sample sequencer 3 initialization for reading in an analog input sample and then converting that into the corresponding digital output for storage or further processing. The flowchart goes like this. We're going to actually start the ADC. We're going to provide the input to the ADC through the sample sequencer, and then we are just going to sort of wait till the ADC remains busy converting the analog input to the digital output. And once it is done and it is no longer busy, then the data is available in the FIFO buffer, and we're going to read data from the buffer. And also we have to clear the trigger flag. Remember, in this case, as we have configured sample sequencer 3 IE 0, so we are really asking the RIS register to notify the end of conversion. Therefore, because this bit is set in the program that we have just seen before, we're going to acknowledge that we are going to acknowledge the notification that the ADC has completed the conversion, and then we are going to write to the bit number 3 of interrupt source clear and the corresponding the bit 3 of the corresponding register to clear this bit. So we're going to clear this bit using ISC bit number 3, ISC register bit number 3. And once and also we're going to read the corresponding FIFO buffer. In some sense, the scheme described here is simply waiting on the ADC to finish converting the analog input sample into its digital value. And so that's just sort of a busy wait program that waits on the ADC, and then when the ADC is done with its completion, we proceed to read data from the buffer. And there are no interrupts involved in this procedure. Now let's take a look at an exact code and how we are going to implement this flowchart. So here is the routine called ADC0 INSEQ3, whose input is wide and the output is a 32-bit unsigned integer. That's essentially the output of the ADC to be stored in a 32-bit register, although only 12 least significant bits carry the result. So inside this routine we have a variable data that is going to be returned, that is going to carry the output of the ADC, but we need to look at how the data is going to be updated. The first instruction in this routine is the initiation of the software trigger. So that's how you start the ADC. So remember, this PSSI register is used for software trigger. So if we want our software, our code to trigger the ADC or to start the ADC, we want to start the ADC, that instruction is going to start the ADC or initiate the trigger or trigger the ADC, essentially triggering sample sequencer 3. Then the next instruction is just waiting for the RAS flag, that is the notification that we receive, and till we get the notification we are going to stay on in this instruction. Essentially this is a while loop which actually does nothing, so it's an empty while loop. This loop will keep on executing until the trigger flag is set to 1 internally by the hardware. So if the trigger flag is 0, we remain in this loop, do nothing. So the microcontroller or the microprocessor is kind of stuck in here, and that corresponds to the busy status. But eventually, the ADC will finish the conversion, and data can be read from the FIFO buffer least significant 12 bits. So that's your data. It has so this data is an bitwise AND of the least significant 12 bits set to 1, this constant hex triple F, and the FIFO buffer value, which is a 32-bit, and only 12 bits carry the output of the ADC. Once the data has been updated, it is now time to return this to exit this routine and return data. But before that, it is important that if we intend to use ADC to digitize the next sample, it is important to set the corresponding bit in the RAS. It has been set to 1. That must be cleared to 0. How do we do that? We write to the corresponding bit of the ISC register, this time bit number 3. So we are going to set bit number 3 of the ADC0 ISC register, and that is going to clear RAS bit number 3. And afterwards, we can safely return the data and exit the routine. With the tools that we have learned in our lecture today and the sample programs just described, we can think about constructing a data acquisition system using our microcontroller, in which there is a main program which is going to utilize the SysTick timer interrupt service routine, such that whenever the timer overflows, whenever the timer completes its countdown, it triggers the ADC. And by the way, ADC, the main program also calls is also going to initialize the ADC driver. Anyways, so whenever the timer generates an interrupt, it will trigger the ADC, and the ADC, once triggered, is going to read the sample available on one of its channels, or the way it has been configured, and then store it somewhere and possibly display it on the LCD. So if you want to display the value of the digitized sample, you might also want to initialize the LCD and write a separate program to implement the LCD driver. With that in mind, there's a homework exercise for you. Write a program and the accompanying interrupt service routine that is going to trigger ADC at regular interval using the SysTick timer interrupt. So you're going to write down the ISR for the SysTick timer that is going to trigger the ADC. And once the ADC has outputted the digitized input sample, you're required to store the cumulative sum of digitized samples into some microprocessor register. From the perspective of thread synchronization, a topic that we haven't really discussed in detail, it is important to note what are some of the threads which are sort of running in the background and those running in the foreground. So in the background, we really care about the SysTick timer interrupt service routine that's executed in the background, which is responsible for sampling or triggering the ADC essentially. And the main loop is a main program, or the foreground thread is a main program that is going to wait for the ADC status and sort of clear the status, and then perform the data storage and processing task, or if you want to display data on the LCD, that is also done in the main loop. From the practical standpoint, the resolution and the accuracy of the ADC are of prime importance, and we're going to briefly outline what are some of the limiting factors which are going to limit the resolution. So it can be a transducer noise, that is the noise entering the analog input sample from the transducer. And the electrical noise, there are so many sources of electrical noise, and then the ADC precision can be software jitters and software errors. Accuracy, limiting factor, resolution can be the limiting factor over here, the calibration, and the stability of the transducers, among several others. So we're going to end this lecture by briefly describing how to calibrate the ADC. And remember, calibration is a procedure of correlating measured value with the reference or the actual value. Let's take a look at an example. Let us try to understand how can we calibrate the microcontroller ADC. We're going to utilize what we call as the fixed point scaling factor, taken as 1 millivolts. It's very close to the resolution of the ADC. And what we do is that we say that any analog input voltage Vin can be represented or can be approximated as follows: 3.3 times n over 4096. So we get this number 4096 because ADC is a 12-bit ADC, so we know that it has 4096 different digital outputs, and then we have in the numerator the value n. So this is the n is an integer, so n is an integer between 4096 is an integer 0 through 4095 for 4096. So this n defines the it's kind of define the digital output, so that you can convert this integer to a binary number. So you can convert this integer into a binary number. It can be one of those 4090 so possibilities which lie between 0 through 4096. So in a sense, if n, let's say if n is 100, then we are really talking about 330 divided by 4096. This much is the value of the analog input voltage. So really what we are doing over here is that we are representing the analog input voltage as a rational number. That's all what we are doing here, and that's the whole idea of the fixed point representation. So this fixed point representation of Vin is important as far as the calibration requirements are concerned. Once Vin is expressed as a fixed point number or the rational number, then it can be represented as I variable multiplied by the fixed point scaling factor 0.001. And our job will then be to relate this I with n. So here is the idea. We equate these two equations containing Vin on the left hand side in both equations. We get I equals to 3300 times n divided by 4096. And what when we are doing the calibration, we input a known voltage. So this first column is actually containing the actual voltage that we know has been inputted. So this is like a reference. And then for each inputted reference voltage, we measure I and n. Now remember, I is the value of voltage in millivolts. So when the units, so the units of I, so maybe I should write it down over here. The units of I are in millivolts. So then we are going to measure. We are going to measure the output of the ADC, which is n, and it has been represented as a decimal number, can also be a binary number. So for the sake of simplicity, this n is represented as a decimal number. So remember, this n or this n is the output of ADC. So we have, for each value of V in, we have this output n, and we also have this I. And how do we get this I? Well, so this I is basically this is just V in multiplied by 1000. So this I is just V in multiplied by 1000. That's it. Then we are going to plot I against n, and the calibration step, the most important step over here, would be to determine a straight line which passes through all of these, which is the best fit representation of the data shown by the crosses. So we have several different points which are plotted on this graph relating I with n, and our job in the calibration is to find the equation of a straight line which can be fully specified by means of a slope and the intercept, and that is going to relate I with n. And therefore, once we have obtained the equation, then we know exactly for what. So this I really corresponds to V in, the actual input voltage. So we know, so after the calibration, after correlating the actual voltage with the measured voltage, and actual voltage is V in, we know exactly what should be measured value corresponds to the actual value. So for each measured value, let's say over here, so for each measured value we know exactly well, this measured value can be some point on this line which is not shown here. So for example, it can be some point over here. So if we get some n over here, which was not previously among the set of points shown here, then we know exactly, once we have the equation of straight line, what is the corresponding V in. We know exactly from the information of the straight line that we have learned as part of the calibration procedure. This is the end of our lecture 8, and I hope that you enjoyed watching and listening to this lecture. If you want to ask questions, you can drop me an email or ask CR to organize a follow-up Q&A session. Till then, stay safe, and I wish you all happy Eid Mubarak. Thank you very much.